Hello, this is a list of nodes which we are going to discover in this lesson. These nodes are very basic and you will use them almost all the time, so we'll start directly with them. Okay, let's get started. Now we need some geometry. Double-click and dive inside. Let's choose a polygon, then put a frequency to 30. Now let's type a VOP. As you can see, there are many geometry VOP nodes, such as point VOP, primitive VOP and vertex VOP. These three nodes are just presets of one single attribute VOP, the only difference is the geometric attribute class is already assigned. So I'm going to use the attribute VOP almost everywhere. Select the class of geometry attributes, which we are going to modify. Then plug the geometry to the first input and dive inside. Inside VOP context, you will find these two nodes. The big one provides outputs that represent all the global variables for the attribute VOP network types. The small one is a simple placeholder to write out common attributes from attribute VOP's network types. Now let's create an add node. This operator outputs the sum of its inputs. Connect P to the add node. P is a position of each point. Now let's connect sum to the output P. As you can see, nothing has changed because we still don't add anything to the position vector. Now let's create a constant node. This operator outputs a constant value of any vex data type. The constant node by default creates a float value. Let's specify it as a 3-float vector. Okay, let's add this vector to position. Look, now we can move the sphere as we like by changing this vector. There is a more efficient way to create constant node. Let's delete this one, then right-click over the second input and choose a constant. Houdini automatically creates for you the constant node. Just specify the type. Okay, let's delete it again. Now I want to continuously move the sphere upward during animation. For that, let's create a float to vector node. This operator converts 3 floating point values to a vector value. These 3 values can be used to represent positions, directions, normals or colors. Plug the output vector to the second input. Then plug the time to the y component just to move along the y-axis. The time is a global time at which the volume is being evaluated. Now let's run the animation and see what we get. The sphere moves up because the time drives y component of the vector. Plug to the x component to move the sphere in x direction or along to z direction. To increase the speed, we can multiply the time by a value greater than 1. Let's create a multiply node. This operator outputs the product of its inputs. Connect it to the time. Now let's create a constant node and multiply by 5. As you can see, the sphere moves 5 times faster. To slow down, you must multiply by value less than 1. Now the sphere moves 10 times slower because we have multiplied by 0.1. Another way to slow down motion is to simply divide the time by a value greater than 1. Let's delete these two nodes and create a divide node. This operator outputs the result of dividing each input value by the next. Let's create a constant value and divide by it. Now the sphere moves 5 times slower because we divide the time by 5. There is a more convenient form of multiplication or division for this type of simple math operations. Let's delete these two nodes and instead create a multiply constant node. The multiply constant node represents a simpler version of the multiply operator because it does not require a second input. It is ideal for scaling a value by a constant. The same applies for the divide node and called divide constant. Okay, let's delete it. In case if you want to reverse the direction, you have to multiply by negative value. There is also a separate node for such a simple operation, which is called negate. Let's create it. This operator negates the incoming value. It simply represents a simple version of multiply constant node, which performs a multiplication by -1. Now let's do the same thing in a different way while learning a few other nodes. First, let's delete all these nodes. Then create the vector to float node. This operator unpacks a vector into its three components. Actually, this is the opposite action that does the float to vector node. Now let's wire up a position. Then create a float to vector node and connect accordingly all these vector components. And of course output vector to P. Nothing has happened so far because the position vector has not subjected any change. Let's create an add node. Then connect the y component of the position vector to it. Look, the y component goes through an add node. This means we can add any value to it. In our case, it will be time. Now let's run the animation and see what we get. Here we go, we have the same result but implemented slightly a different way. Let's change the direction along x-axis. For that we only need to connect x component instead of y. That's it, the sphere moves along the x-axis. I also want to introduce you the subtract node. Let's create it. This operator outputs the result of subtracting all its inputs. It means after subtraction the sphere will move in the opposite direction instead of adding. This is simple math, I just want to introduce you to subtract node. Here we go, the sphere moves in the opposite direction. There are also simple forms of these two nodes, called add constant and subtract constant, which do not require a second input, it's already built into it. Okay, I also want to introduce you two more nodes. Let's create the first of them, which is called a set vector component. This operator assigns a value to one of the vector's components. In this situation it can completely replace the float to vector node because we modify only one component of the vector. Now let's create the second one, which is called the get vector component. This operator extracts a vector component. In this case the get vector component can completely replace the vector to float because we need to extract only one component of the vector. Okay, let's connect a position to it. Then specify which component to extract. We will select the component 2, which is the y component. Then plug it to the first input. Let's also get rid of these two nodes. Connect the difference to the vector component, which needs to be changed. Give it a position vector. The modified position goes to the output P. As you noticed, something strange happened with the sphere because we forgot to select the y component. Here we go, now we have the same result. Let's also reverse the direction simply by adding the negate node. To change the axis along which the sphere moves, you just need to change the vector component of these two nodes. That's it, the sphere moves along the x because we select the first component. Now let's do something more interesting based on this concept. First let's delete all these, we no longer need them. Let's type a noise and choose a turbulent noise. This operator can compute three types of 1D and 3D noise based on point position. Let's also create an add node because we are going to add a noise to the position. Connect a position to it. Look, the noise output float value because by default is selected 1D noise. Let's select 3D noise. I also want to change the type of noise. Select the original Perlin noise. Now we can add the noise to the position. Look, the sphere has been deformed. Let's adjust the noise settings. Look, sliding the offset moves the noise. Now I propose to drive the offset by the time. We have already done something similar. Let's create a float to vector. Connect the output vector to the offset. Then connect the time to the Y component. Now let's run the animation. Here we go, the noise moves along the Y-axis. We can also replace the float to vector node by set vector component, which we already know. Connect time to vector component and the output vector to the offset. Delete this one. Now let's select the second component of the vector and run the animation. Nothing has changed, the result is the same. Okay, that's all for this lesson. In the next lesson we are going to discover the big list of new useful nodes, as well as already familiar nodes, but in other circumstances. See you in the next lesson.